So in the last class, we covered support vector machines, SVM. This class, we will do a little bit of support vector machines. We'll try to code up one, or we look at the code of one specific model. And then we will also try to code one by ourselves. We will not do SVR. In fact, we will do AR in this SVC class. We will revisit support vector machines again and again in this class. And there we will try to code up a SVR, a regressor, support vector regressor, along with another code for SVC. Okay. In today's class, we'll just try to do one small simple example for support vector machines. We'll see one and we'll try to do one. Okay. And again, the next class is kernel tricks. We will discuss more about like applying support vector machines there. We will do bias variance. We'll try to cover bias variance trade-off as well today. It's a very important concept in machine learning, and it's a very important interview question. I want you guys to like keep that in mind. So if you do go to interview for a data scientist role or something like that, you will definitely be asked this question, bias variance trade-off. If you're going for a proper data science role, this is a question that will definitely come. So it's an important concept, and it helps you like understand the trade-offs that are there between various models of data sciences and like which one to go, in which case, what to do, and so on, right? And it's something that is not avoidable, and that's the reason why we call it as a trade-off. You either have high bias or you have high variance, right? So, but you can find a sweet spot between this trade-off, and that's basically what optimization of models basically means. Optimization of accuracy or point or a model or a problem statement basically means, right? Okay. Now let us quickly go back to our support vector, not this one. Let me go into this notebook. Yep. So let us go back into our notebook. We saw this notebook in last class. We went through this notebook a little bit. We didn't go through the code itself, but we did go through the concepts within this notebook. So we will do a quick revision of some of the major concepts. We will also try to look at some examples, and then we'll move on to code. I want you guys to also like pull up a Jupyter notebook locally. I hope you guys have Jupyter notebooks installed. I want you guys to follow with me and do this, because I will give it as an exercise. I will not give you the whole code. I will give you a piece of the code, and I want you guys to like try and implement it. In last class, I kind of told you a couple of points about this image. We'll go over them again, okay? And just as a recap, right? Support vector machines are, let's say they are machine learning models that you would use, and you can do both supervised learning problems. You can solve both supervised learning problems, which is classification and regression, using support vector machines. If you are doing regression, the model you would be using is called SVR. If you're doing classification, the model you would be using is called SVC, a support vector classifier. Okay. Now, where does this, what's the concept of a SVM? And what's the whole model itself, right? So whenever you apply a support vector machine, you are trying to find a function which best describes or best solves your problem, right? So assuming that you're trying to do classification, right? Classification itself means dividing the two distinct groups, or finding two distinct groups in your data, and then drawing a line or a decision boundary or some kind of a device, say a dividing line across these two groups so as to separate the data into two different groups. Okay, and that's exactly what is happening in this particular image that you see on screen, right? It's a support vector classifier that you're seeing here, right? So again, going back to what is a regression, what is a classification? A regression, you're trying to predict labels or categorical labels, right? Classification, you're trying to predict categorical variables, right? The target variable is categorical in nature. You're either saying whether my data point belongs to bucket A, bucket B, bucket C, or something like that, right? Regression is when you're trying to predict a number instead of a categorical variable, right? You're either trying to predict what could be the height of my next basketball player, or what would be the amount of rainfall I would receive on any given day, or something like that, right? it's a number. At the end of the day, what you're trying to predict is a number. In case of regression, what you're trying to predict is predict if it's a label or a category, that is classification, right? So in this case, what you're seeing on screen right now is a SVC model, because there are two groups of data, right? So there are orange points, right? And there are green points here, right? So, and then this separating hyperplane. Okay, let me start screen right to quickly annotate. Okay, and this separating hyperplane that I have here, right? This line that I have, it's trying to divide these two groups. This is group A per se, and this is group B. Okay, it's trying to divide these two sections or groups of data and say that, okay, these all points belong to group A, these all points belong to group B, right? Now, again, you see some overlaps, right? Two green points are in this upper group, two orange points are in the below group, down group, right? Those are the anomalies that you have in the data, right? You cannot always perfectly divide data. There will be some overlaps that are available, right? Now, this itself is my model, okay, or this is the line that is basically helping me. So after I draw this line, right, after I find out the equation of this hyperplane, what happens, right? Now, if I get a new point here, it will predict that this point belongs to group A. If I get a point below the line somewhere here, it will predict that the label for this point is group B, right? So that is basically what is called, what is my decision boundary or separating hyperplane, right? And in last class, we also discussed that we are calling this as a separating hyperplane, right? But what exactly is this in this case?
The hyperplane?
Yes, the hyperplane. This is, so there are two dimensions, correct? And what did we discuss? How many dimensions would a hyperplane have? If there are n dimensions in my data?
Two.
Yes. So there are n is two in this case, Susan, right? So we have two dimensions. We have two features. There is X, there is Y. Okay. So there are two features in my data set, two columns in my data set. So how many dimensions is my hyperplane in this case?
One.
N minus one.
Yes, Obi and Susan, both of you are correct. So if we have n dimensions in my data, my hyperplane will always be n minus 1. Okay, so let's say if I have 5 dimensions, my hyperplane is going to be a 4-dimensional hyperplane. Okay, let's say if I have 3 dimensions of in my data set, right? I have 3 variables, which is X, Y, and Z, right? My hyperplane is going to be a 2-dimensional plane, a simple plane. Okay, so in this case, it is 1-dimensional and it is a line. Now, how do I draw the line itself? I draw the line using these 2 dashed lines, which are called support vectors. And that's how SVM gets its name. Okay, these 2 dashed lines are support vectors. How do I get the support vectors? How do I identify the support vectors? I look at the boundary points of each group and I try to identify a space, right, between these 2 dashed lines, which does not have any points, any observations, right? Because I'm trying to find empty space through which I can run my plane and then divide the data set into 2 categories or multiple categories.
Question.
So to say. Yes, Obi.
So how do you get your support vectors? How is that generated?
Yes. So they are straight lines that are drawn, straight lines or planes or whatever they are, right? So in this case, it's a straight line because we only have 2 dimensions. We have a straight line, right? So the support vectors, yeah, this is a good point. The support vectors are also n-1 in nature. Okay. Not just the separating hyperplane, my support vectors also would be n-1 in nature. In this case, since I have 2 dimensions, my support vectors and separating hyperplane are all n-1 dimensions, which means they are straight lines, single dimensional entities. But if it's a three-dimensional space, right, my support vectors are nothing but support planes, right? There'll be two-dimensional planes, and then there'll be another plane between these two planes, which is called my separating hyperplane or decision boundary, right? Now, how do I arrive at these lines themselves, right? How do I draw these lines? So here in this green group, right, that you observe, let me erase the stuff that's there on the screen because I want to redraw. There is there is a clarification image that I want to give, because although this is a separating hyperplane, it's not the best separating hyperplane you can draw for this data. So let me quickly illustrate what I mean. Okay, so if I have a regression model, okay, let's say these are my points, okay, for my regression. So if I can draw a line, or I can fit a line like this, I can fit a line like this, I can fit a line like this, I can fit multiple lines, correct? But what is the best line of best fit? If you guys remember linear regression, right, the line of best fit is that line which is equally distant from all these points. Like, it's trying to minimize the distances, right? So these distances, it's trying to reduce that distance, right? Actually it should be straight in nature. 1 second, it should be like that. It's hold on, yeah, it's these distances, right? It's trying to reduce these distances, the
But
total sum of.
it doesn't happen to be the case for the green category green objects or points.
Correct. So that's the reason for, in this case, right, this in this figure, this is not the best hyperplane. That's what I'm saying, right? It's one of the hyperplanes, but it is so far away from this group, correct? Again, this is not regression, this is classification. So we are not trying to minimize the error that way. We are trying to minimize the number of classifications it does, right? So it is still a good classifier, but probably not the best, right? The best one, because the support vectors in this case itself are drawn not in a great way, okay? Although this is correct. So let me explain. So how do I draw my support vectors? How do I come up with my support vectors? In this group, right? In this group B that I see here, all these green points, right? What are some of the border points that you see of this group? These 2 points, right? Of this group. All the other points are below these 2 points, right? So if I draw my dashed line here, right, I have a space underneath this line which has most of my green points, correct? Now, in the same way, for this orange group, right, this dashed line should ideally be here, because these two are the border points for me,
Correct.
right? So when I do this, all the other orange points are above this line, right? So these border points, right, these observations which are on the edge of the dimension space, when you run a line or a plane or some kind of a divisive entity, right, through these border points, what you get are called support vectors. Okay, now once you get these support vectors, what do? So I got this support vector here through these border lying orange points. I got this support vector here through these border lying green points. Now I have this space in between them, right, where there is nothing. There are no observations, right? Then I draw a line midway through the space, which is equidistant. If this is D, this is also D, right? Which is equidistant from both these dashed lines and it's parallel to them, right? This becomes my hyperplane. Okay, and it is also called as a decision boundary. right? Why is it called a decision boundary? Because any points above this boundary will be labeled as A or orange, right? Any points below this boundary will be labeled as B or green. Make sense?
Yes.
The reason why we separating upper plane is not a perfect diagonal, is not starting from the middle. It's
Which, the previous one, you mean?
one of a separating upper plane.
Mhm.
Yeah, any reason why it's not a perfect diagonal? It's not starting the field in the middle.
Oh, in the previous case, you mean?
In this case, what I'm saying right now.
Oh, if you're considering this one, right? This is the correct hyperplane.
It's separating.
I think he's
upper
talking
plane.
about that the orange dots. Why is the support vector not cutting through the border points?
1 second. Let me erase all of these. Let me make things a little bit more clear. Let's go over this again one more time. So
Because here we're separating upper plane. You see?
yes, correct.
So my question is that why is that is not cutting from zero, from that 90-degree angle, and is showing up the x-axis?
You mean to say something like this, is it?
Exactly. Any reason why?
Okay. No. So see, do not think about this particular line to be having to start from the origin. It doesn't have to start from the origin. Okay. It's some line, right? If it's starting from the origin, then this is a line with a specific equation. But okay, if I have to explain this, right? This line completely depends on where my data lies, right?
Okay.
So my data, right, the orange points that I have here, if I'm assuming that this is group A, or let's say for the sake of clarity, I'll call this as group orange. Okay, and I will call this as group green. Okay, my orange group, right, if you see the points themselves, right, they are spread all the way until this point, right, here unto here, right? And where do I have my empty space? My empty space is somewhere here. I cannot get to my empty space if I am trying to draw a line here, right? I'm cutting through the cluster itself or the group itself, right? So it is not necessary, or there is no requirement that the plane has to pass through an origin. It can have any intercept, right? It can have any intercept. It can be anywhere. It completely depends on where my data lies in the coordinate system. Okay. Does that make sense?
Yes.
Cool. By the way, SVC clear at up to this point? Any questions?
I got a question. You say
Sure.
that the dimensions can be n minus 1, the number of variables. So does that mean that an SVC can have as many variables as the number of, no, I'm sorry, it can have as many dimensions as there is number of variables minus 1. So there's no upper limit on what the dimensions can be.
Right. So if you are talking specifically about your data set, right? So okay. So n is basically the number of dimensions. Basically, that means the number of columns your data set itself has, right?
Yeah.
So let's assume that I have a table which has like so many columns, right? C1 is column 1, column 2, column 3, column 4, so on, right? Up to column n, right? So there are n columns in my table. This is an n-dimensional data set.
Yeah.
Data set. Okay. Now, So what I mean by n minus 1 is it is the number of dimensions that my separating hyperplane will have. Okay, so what I mean by that is you're looking what my separating hyperplane is basically a function, right? At the end of the day, it's a function, right? It's a function which denotes either a line or a plane or a three-dimensional entity or something, right? It is something that helps you divide your n-dimensional data into groups or fits through your n-dimensional data if it is SVR and helps you predict, right? So when you have n dimensions and you apply a support vector machine, you're building a support vector machine, your function ends up having n minus 1 dimensions. Okay, to last class I gave an example for that, right? So what is the equation of my straight line? The equation of my straight line is mx plus c, correct? Right? So how many variables are there in this equation? There is only one variable, which is x, correct? M and c are my coefficient and intercept, which are actually my constants, right? Once I find a function, once I find the equation of this line, right? In a linear regression problem, let's assume in a linear regression problem, what is the at the end of the linear regression, you fit a line to your points, correct? And when you try to print out model.coefficient, it will give you the value of m for that particular line. And if you print model.intercept after applying linear regression, it will give you c, right? So those two values itself remain constant, but the single variable that you have here is x, right? And you're trying to predict y given value of x, and that's why y is equals to mx plus c is your function, correct? So this is f of x. Now, assuming that I have x, y, z, w, q, whatever number of features I have, and I'm trying to predict y, right? So y will be a function of x, z, w, q, and whatever predictors I have, right? So now what happens? I am removing one variable out of it. How many variables am I using, right? If I'm trying to predict a single variable here, right? How many variables will I have here? My function will have n minus 1 variables, right? Or n minus 1. And that's exactly what I'm trying to say, that this function or this hyperplane that you get is always going to be n minus 1 in nature. Okay. So does that answer your question, David?
Yeah.
And to give you a much clearer idea, if this is a two-dimensional system, right, x and y, so your hyperplane is a one-dimensional entity and one-dimensional entity is a single line, right? So in the same way, if your function or if your dimensional space were to be a three-dimensional space, you would end up having a plane for a hyperplane. Now I'll show you what that would look like. Okay, because last class I was kind of telling you guys about three-dimensional plots, right? So let us look at, okay, let me close this. Let us, oh, sorry about that. Let's look at this simple diagram, right? This is a good one. Okay, it's KD nuggets, separating line, separated axis. Okay, see. So here, right, as hyperplane in R square is a line, right? R square meaning a two-dimensional space. Okay, it's a line. A hyperplane in R cube, which is a three-dimensional space, is a plane. So you see this, it's a plane instead. That is separating these two data points, because in this is a three-dimensional space, this is a two-dimensional space. Now, what happens in 4 or 4+ dimensions? Obviously, we can't draw a plot like this because we can't perceive 4-dimensional objects. Human beings can at best perceive 3-dimensional objects. That's a limit of our perception, right? That's why we don't have it. But you can abstractly or theoretically assume that if it's a 4-dimensional space, the division or the dividing hyperplane is going to be 3 dimensions, right? So if you have 5-dimensional system, you will have a 4-dimensional plane, and so on and so forth, right? So thinking about it, right? If you have n dimensions, your hyperplane will always be n-1 dimensions. Does that make sense? Intuitive enough? Do you guys understand this figure? Any questions about this?
Classification.
Yep. Awesome. Good. So see, possible hyperplanes. This is another good diagram, right? So possible hyperplanes. So these are all the various ways with which you could divide the two groups. But what is the optimal hyperplane, right? The optimal hyperplane is when you draw these dashed lines. These are the support vectors. In reality, you won't be drawing them, right? You're just applying the model. On the back end, what the model itself does is it looks at boundary points. It runs a couple of lines or planes or whatever entities through these boundary points. It finds maximum margin, right? This empty space where there is no observation. It finds that empty space. Then what it does is it draws another line or plane or whatever object, right? A decision boundary between these support vectors, which is equally distant from all these support vectors, and then groups your data into multiple. So again, so awesome. They have a 3-dimensional GIF as well. So this is how it would look like in 3-dimensional space. Okay, so that plane, that red-blue plane that you see in between, that is dividing this group of red points and group of blue points, that is the hyperplane. Okay, now what would happen? This is in case of classification, right? What would happen in case of regression, right? So you will have, instead of these colored points, you will have a single set of points, because there you're not trying to group data into multiple buckets, right? There you're trying to fit a line that best follows or best describes or cuts through the points in such a way that it minimizes the error. And error means how far is the point from the plane or the line, right? Or how close is it, right? So there the plane will be passing through as many points as possible, or will pass through these points as closely as possible, so that it minimizes the distances between these points and the plane itself. Does that make sense? Let us see if we can actually find a support vector regressor. Yep. So let's look at this. This is a good picture. Let me move this here. Okay. So see this is an example of the support vector regressor, right? Here, what's happening? How are my support vectors actually, what are my support vectors actually doing, right? They are again looking at boundary points, right? But this time they're trying to do the reverse of what it did in classification. In classification, what were the support vectors trying to achieve? They were trying to find space where there were no observations. In support vector regression, the support vectors try to find as many points between them, between the space that they have, as possible. They'll try to fit as many points as possible. So see, this line is basically passing through one of the border points with, and then another support vector, right? Again, passing through a border point and making sure that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 points, right? Which are within these, and then 1, 2, 3, 4, 5 points beyond these things. In fact, this line could probably come slightly here and then increase it. But again, though these lines basically depend on how far am I moving away, right? From other points, what could my distance be? Because a regression line, right? Like how many points is it cutting through? So if this line, dashed line, were also passing through these 2 points, then this line here might shift a little bit towards the bottom. So let me draw this and show it to you guys. Yep, cool. So assuming that this dashed line, right, on top, were here, right, so that it is incorporating these 2 points as well in between, right? So what happens is I'll have now 11 points between these two dashed lines, right? But what happens here is this line might actually move down here. This red line might actually be somewhere here because it has to be between these two dashed lines, right? And when it comes down, these 4 points might no longer fall on it, which means there will be a real error, right? There will be a real error between these 2 points. So that might actually maximize the error. And what are we trying to do in regression when we are trying to find the line of best fit or the plane of best fit? We are trying to minimize the error to the extent possible, right? So we are trying to see the line, if it passes through as many points or it passes as close to as many points as possible. So in this case, probably that's why the dashed line is slightly above. Even if it lets go the other 2 points, it has the line passing through the center, and that becomes the line of best fit. So this is a support vector regressor. That red line that you see in between is a support vector regressor. And the support vectors, which are the dashed lines in a regression problem, they try to accommodate as many observations, as many points between the space that they have as possible, so that the line passing through the center has as less error as possible. And more so the support vectors, right? They try to accommodate as many points so that this is, in this case, it wouldn't be called as a decision boundary, but it's probably the line of best fit, right? Or the plane of the hyperplane that's best fitting the data, right? It accommodates as many points as possible between the space that they have, so that the line passing through it is closest to these points.
So
It reduces the error.
is there an expression to calculate the support vector, or is something you just draw randomly?
Right, there is an expression, there is formulation, there's a lot of science that goes behind drawing these support vectors. But again, you don't have to worry about it because you are not going to calculate the support vectors itself, right? All you're going to do is call the SVC method from sklearn library. This is the back-end working of what the algorithm actually does.
Sounds good.
Okay, so it hypothetically draws the support vectors for you, because the way it arrives at this function, at this model, is by drawing these support vectors. Okay, so the reason why I'm explaining this concept to you is, in an interview, right, they will ask you like, hey, SVM, can you tell me what support vectors are, right? You guys need to know that these are lines or planes that pass through the boundary values in a distribution or in a data distribution, either find the space or the empty space between two groups of data in case of a classification problem, or to find or accommodate as many observations between them as possible, so that the line of best fit or the plane of best fit passes through these points as closely as possible, reducing the error of prediction. Cool. Let me ask you a question. What is this in this case? Is this a SVR or an SVC?
SVC.
Okay. Does anybody think anything else?
You mean this
I think
one?
it's SVR.
It's SVR.
What are you pointing at? I don't even know. I can't.
This figure.
It's
This is-
SVR. I think you're
that you
giving
see.
yourself away because the
SVR.
label says SVR right there.
Okay, aside from the label, but we should know that it's FGR.
That's a trick
Right,
question.
right.
That's a trick question. It says SVR, but it's actually an SVC.
Interesting. So Google
Right?
is wrong, basically.
No. Google probably might not. See, again, this is an image that is being pulled up from an article. They might be writing about SVC, but they are definitely talking about an SVC. They might be writing about an SVR, but they might definitely be talking about SVC. So let's look at this actually and see. But it's definitely an SVC, right? They might even be wrong, but I don't think they are wrong. I hope that, yes. So, okay. So it says SVR, they are wrong. Okay. So this is actually, I guess, like a group of illustrations that are being sold. They are wrongly tagged. Okay, so the reason why this is an SVC, support vector classifier, is because if you see these two dashed lines, right? Let me go back so that we can see just the image, right? So this one. Let me close this. Yeah. So these two support vectors that are there, right? What are they trying to do? These are all blue points. These are all green points, right? And they're finding an area between them both, these two groups of data, and this red line, which is the decision boundary, is trying to group these two data points into two different categories, right? Which is a blue category and a green category. Next time when it encounters any new point, if the point is above the red line, it will tag it automatically as a blue point. If it is below the red line, it will tag it automatically as a green point. Okay, does that make sense? This was a trick question, by the way.
And that looks like it would make a better image for the one you were talking about in the notebook, the first one.
Yep.
That's how you drew it.
Correct. So this is definitely a better image, because in the notebook, right, the issue with the what we have in the notebook is that this is not the best hyperplane, right? Remember the another figure that we kind of saw where there are multiple hyperplanes that are possible. You can draw many. So where was that? It was a KD Nuggets article. Let me actually collect these. Yeah, this was the one, I guess. Is this the one?
Okay, so basically, I think we are seeing three kinds of support vectors. We have the regression, we have the classifier, and they have the machine.
No. So support vector machine is a general term. That's a good point that you brought that up. Support vector machine is a general term, right? So there are two types of machines that you might have. One machine is a regressor, the other machine is a classifier. Okay.
Yeah, but some of the objects are explicitly labeled support vector machine. Some are labeled classifier and some regression. That's a little confusing to me though.
Right, but think of it as, so an SVR is also a support vector machine. An SVC is also a support vector machine, right? Both of them are support vector machines themselves, but one of them is a classifier, one of them is a regressor, right? You can call them both SVM, right? But underneath, right? So if you think about supervised learning, right? Regression is also supervised learning. Classification is also supervised learning. Both of them are supervised learnings, but one type of supervised learning is regression. Another type of supervised learning is classification. In the same way, one type of an SVM, a support vector machine, is a classifier, which is an SVC. Another type of an a support vector machine is an SVR, a support vector regressor. So once you implement them, right, you will get much more clarity because there are specific methods. So when you implement a classifier, you call it SVC. When you implement a regressor, you call it SVR. That's where you will clearly understand. When you look at the code, you can clearly tell whether a support vector machine is a classifier or a regressor. Does that make sense, Obi?
Yes, sir.
Yep. So here, right, again, different hyperplanes. All of these are classifiers. All of these are dividing these two data points into the red squares and the blue circles, right? So think of this line, it's still doing the job. This line is also doing the job. That other line is also doing the job. All the lines are doing the job of classifying your data into two groups. But which one does the best job, right? Because, so what happens if I draw a line like this, right? I am annotating again. What happens if I choose this line as my best line, right? So I am assuming that, let's say if I get a point, say here, right? If I have a circle here, because my line is vertical like this, right? I might actually misclassify this as a red square. Okay, although it is actually closer to these points, right, than it is to these points. It is closer to the blue circles rather than being closer to the red squares, right? So in the same way, right, let's assume that I have a square here, right? But because I chose this line as my boundary, I might wrongfully classify or wrongfully predict that this is a blue circle instead of a red square. Are you guys seeing the danger here of picking a wrong line, of picking an inappropriate line? Right?
Yes. So in your opinion, what do you think is the best line?
Exactly. So that's where you would look at, and that's where SVR tries to find the best line by drawing these support vectors, right? In this case, it draws these support vectors in such a way that it finds this maximum margin, right? The maximum space and the orientation, right? Orientation also is important. Orientation of that space, right? It tries to find what's the maximum gap that I have. And in trying to find this maximum gap, it finds the orientation. And then we get the line here. Now what happens is if I draw a point here, right? I will correctly classify that. If I draw a point somewhere here, right? This is actually closer to this blue group than it is to the red group, right? So you can see that this way, right? When you find the optimal hyperplane in this fashion using support vectors and finding the maximum margin between these two groups, and the maximum margin is defined by the space where there are no observations between these two support vectors, right? That empty space which can be used to draw the decision boundary or the optimal hyperplane. So one quick tip that I would like to give you guys is a general tip. I am posting what I'm posting here, the links that I am using to show these figures, these are actually articles in Towards Data Science. Okay, it's a Medium article. Medium is basically one of online publisher. So they have this blog called Towards Data Science. Okay, I don't know if you guys are aware of that. So a lot of data science stuff, a lot of people write up about data science stuff and then upload their articles or their knowledge on these posts. Now it requires a subscription. So when you click on these links, what happens is these articles might open up, but you have a limit of 3 free articles per month, right? So when you click on the link, it will open up, it might show, or it might block and say that you've already read your 3 articles and then you can't read anymore, you're blocked, you need to take a subscription. In that case, what you do is simply open a fresh incognito window and paste the link there. It will still start counting from 0, 1, 2, 3, 1, 2, 3 numbers. So you can basically read as many number of articles as you want in incognito mode. Again, even in incognito mode, it will count up to 3. So you have to open a fresh one to restart the counter, okay, every time. So that way you can basically read through as many articles as possible without having to pay for it. We will go through the notebook example itself, okay? A pretty simple example. And then what we will do is we will take the iris data set. Again, it's the same thing. We will take that and we will try to implement a couple of models. Basically, it's the same one. We will try to do it on our side. Okay. All right. Are you guys familiar with the iris data set? Does it ring a bell? You remember seeing it somewhere?
Yes.
Cool. Awesome, Susan. Anybody else? Awesome. Liz.
Susan has seen it and I've seen it too.
Okay. So can anyone explain what the iris data set is?
Isn't it where they try to classify the flowers based on the stem size and the petal size?
Yep. So that iris dataset basically has about, I guess, 4 different types of iris, 4 different features. I think there are 3 different types of iris species in that dataset per se. There are hundreds of types of iris flowers out there, but this particular dataset has 3 different species of flowers. And the reason why it's a very good data set for learning these kind of things is to play around with it is basically these three flowers are kind of very distinct to each other in the petal and sepal length and width. All right. So those are the four features that you will be able to see in this particular data set: sepal length, sepal width, petal length, and petal width. Right. So petals, let's just quickly look at iris petals and sepals. Okay. Yep. So if this is my iris flower, right? So the sepal is this long one, is this big one, right? And the width is this. The length is this one, right? This vertical dashed line. The blue vertical dashed line, the blue dashed line is the petal length, and the blue solid line is the petal width itself. Again, no surprises. This is the iris classification demo from SnapLogic. If you look at the link there, right? So it is talking about classification problem, applying the classification model to this data set, and the figure is basically shown as an example to explain that. Okay. So this is my data set. So I have three different types of, so each species of these flowers. So there are three different species in the data set that we have. Each species has a different sepal length and sepal width and petal length and petal width. And that's how you can identify which species a particular flower belongs to. And that's the what do you call objective of the classification model itself here. Okay. Now going back to the notebook itself, right? So in this case here, right, in this example here, so the first line of code is basically just a matplotlib inline. This is just making sure that the matplotlib charts themselves show up in the book below the code block. These are a couple of library imports. This is a linear SVC model import. This is datasets from sklearn. This datasets import, the reason we do it is because the iris dataset is available in the library as a pre-built dataset. Okay, so once we do this import line, in the first line after the imports, what we do is iris is equals to datasets dot load underscore iris. And can anyone tell me what this is? What does this look like? Does this look like a data type? Does this look like a variable? Does this look like a library? Or does this look, what does this look like? Or a decision statement? What does this look like?
Load iris, isn't that like, it will load like the data, no? The data frame?
Correct, that's what it is. But what does parenthesis mean? So this is what type of a, from programming standpoint, this is what I'm asking.
Function?
Sorry? Yes, absolutely, Ubi, that's correct. It's a function, right? And it's a function in this module, in the datasets module of the library, sklearn library. So you're calling this function, and when you call this function, what it does is it picks the dataset, that the iris dataset that we have, that it has in memory, and then it stores it in this variable iris here. Okay. Then what you do is, you know that here in this case, right, you're picking two variables. Okay. So up to 2 and the first 100 samples, that's what we are selecting. Okay. So as I said, there are 4 different variables in the iris data set, right? 4 different predictors, so to say: the sepal length, sepal width, petal length, and petal width. In this case, we are only taking 2, and you see a 2-dimensional plot. Can you guys tell me like why we specifically picked 2 and not 4? Can you guys think about it now in respect to this visualization, with respect to this visualization? What happened? What would have happened if we picked 4 here? All the 4 predictors that we have, all the 4 predictors, which is sepal length, sepal width, petal length, and petal width. If we pick all 4 columns of the data set, or all 4 predictors, would we be able to get this visualization?
No, we're trying to categorize into 2.
Exactly, right? So we can't build a 4-dimensional visualization, right? We can't build, we can't visualize a 4-dimensional data set, right? And that's the reason why we consciously select only the first two features, so that we can actually plot it and actually see it in a two-dimensional space. So we took this. Now the target here, right? Iris.target. The target itself is a column which has numbers 0, 1, or 2, because there are three categories or three species of iris flowers. Okay, so what target basically tells me is, does this belong to species number 1? Does this flower belong to species number 2? Or does this flower belong to species number 3? Okay, that's basically what the target is basically telling me, right? Now, what will I try to do when I'm framing my classification problem? I'm trying to predict the target, which is the species the flower belongs to, depending upon the sepal length, sepal width, or petal length and petal width the flower itself has. Okay, so those four characteristics of the flower: how long are the petals, how wide are the petals, how long are the sepals, and how wide are the sepals, right? Those four characteristics basically help me identify the species of iris flower, right? And when I build my classifier right here, I'm trying to learn, I train it on the data. Basically, that's my X value. And I'm trying to predict the target, which is my species label. Is it species 1, species 2, or species 3? That's clear to everyone. If you have any questions, feel free to ask.
I think it will be better if we like actually see the data, maybe like the first 10.
Sure.
So that we can...
Okay. I thought you guys were aware of the data set. That's fine. Okay. So this is the data set that's loaded. And see here we have 4 columns. Okay. Sepal length, sepal width, petal length, and petal width in centimeters, right? Because they are flowers, they're just probably this big in the hand, and these people have measured them. So there are 150 of them. Okay. Can you guys tell me what 150 is here? What are all these?
The rows.
Yes, rows, which also means
Flowers.
correct, observations and or flowers, right? So they took about 150 different flowers. They measured the dimensions for each of these flowers, the sepal length, the sepal widths, petal lengths, and petal widths in centimeters, took down those numbers. Okay, and then what we have, okay, this is X, right? This is my data itself. These are my features. Now let me print Y as well. So look at this, 0, 0, 0, and then some 2s at the bottom, right? This is my target. This is my target label, which means species 1, I have a label of 0. Species 2, I have a label of 1. Species 3, I have a label of 2. Again, the reason why we start from 0 is you remember the indices or everything in Python programming, right? It basically starts from 0, right? If it's an index in a list, it starts from 0, 1, 2. So the reason why they encoded it as 0, 1, 2 is because the encoders also work on the principle of these primary data structures, where the indexing numbers typically start from 0, right? So when you use an encoder or something like that to come up with these values, the actual value would be 0, would be some kind of a species name. I can look up, let's look up a couple of iris species names. Right. So, okay. So this is Iris insata thun. Then there is Iris pseudacorus. Then there is Iris versicolor. Then there is Iris virginica. Right. So these three, let's look at these three. The top names are like kind of Japanese names. Let's not get into that. But so if you look at the bottom 3 names, right, there is pseudacorus, there is versicolor, and there is virginica. Right. So these are the actual species names. But you remember, right, like in coding, when you are coming up with categorical variables, models cannot interpret strings or categories. So what you do when you interpret a category and you're trying to train a model on that, you kind of label them with numbers so that the model can actually work with these numbers, right? So imagine that these three were the species. In fact, the bottom two are actually some of the two of the species in the iris data set. I don't think Pseudochorus is one of the ones, but anyways, imagine that these three are the three different species. I will name Pseudochorus as 0, versicolor as 1, and virginica as 2. And that's exactly what you see here in these labels. Okay, so let me do I don't know if this would work. Okay, so if I do unique, right, so I see that there are 3 unique variables or 3 different unique values, 0, 1, and 2 in this particular target variable. Okay, so this is my species 1, which is Pseudochorus, species 1, species 2, which is labeled as 1 again, which could be versicolor. This is virginica. Okay, these are the 3 different species of flowers, and these are their attributes. Okay, and how many flowers do I have belonging to these 3 categories? I have about 150 different flowers that I collected, measured, but they definitely they belong to 3 categories. But the flowers that I actually saw and measured these variables for themselves, that themselves is like 150 different flowers, right? So when you see here, right, like the first 2 variables, first 2 features were basically selected. So if you think about it, so sepal length and sepal width, these 2 are the features that were selected here in this data set. Then there's some standard scalar that is happening. This is an important operation. I'll tell you why later. So, and then we perform these, this is scaling, right? So we are scaling the data set so that we fit all our observations between 0 and 1. We'll talk about that later, okay? Because when we do the exercise, I want you guys to not do this and see what the results are, and then do this and see what the results are, okay? Create support vector classifier, okay? So this is where we are calling our method linear SVC, right? We're calling the classifier C is equals to 1.0. We are setting the error. So C again, okay. So C is a, so there is a concept called regularization. I guess you guys would have studied about that in DS2, right? So does anyone remember like what regularization was? So regularization basically is when, let's say you're applying a model, right? And you've like given a lot of freedom to the model to learn the patterns in the data and then come up with a function, right? Sometimes what happens is the model also learns the noise in the data. Noise means minor fluctuations which are caused by outliers. Okay, to give you guys an example, let's assume that I am looking at heights of different people, right, in the United States. My average height range could probably be from the 4.5 feet, starting from 4.5 feet, all the way up to 6 feet or 6.5 feet even, right? This is my average range because I will find a lot of people between this range, right? But there are outliers, which means there are people who might be shorter than 4.5 feet. There are people who might be taller than 6.5 feet, right? So those, but they are not too many in number, right? But let's say I look at a sample of 100 people, right? And then I have most people falling between 4.5 and 6.5 feet. But I have some people, like let's say about 3 people who are either above 6.5 or below 4.5 feet, right? These people are not common. That is why they are called outliers, right? These are not commonly observed observations, right? These are not commonly occurring observations. So these outliers, when you're trying to develop a model which is learning the pattern in your data, right, it will try to fit for the most general part of your data, which is, let's say if I'm trying to fit a model where I'm trying to predict the height of a person I'll encounter next, right? So if I build a model and let's say among my 100 samples of data, 97 of them are between 4.5 and 6.5 feet, right? If I fit a model, it will try to predict a value between 4.5 and 6.5, a general model, a good model, right? But if I allow too much freedom for the model, then it might learn from the noise, which means it will also try to fit to the person or the people who are shorter than 4.5 or the people who are taller than 6.5. Instead of looking at the general trend, it will look at these outliers as well, and it will try to fit for them. What happens when it tries to learn through this noise and fit for these outliers is, when I find the next person, it might predict, it might give me a wrong prediction. It might say 6.5 or 6 feet 8 inches, or it might say 4 feet 2 inches, because it's also learning from the noise instead of looking at the general pattern of data, right? Now, when my outliers are very less, like 2, 3 in number, that's not really a big issue, right? We can even isolate them and remove them out of the model. But if I have more values, right, which are like varying a little bit, right, high variance, if I draw a much more complex model, it is going to overfit, right? That's what's called as overfitting. Overfitting basically means that when a model fits to the noise in the data, rather than looking at the general trend or learning the general trend in the data, it fits to the noise. Okay. It tries to come up, and such a model, right, will have very high accuracy in your training set, because it has seen every data point in your training set. Let's say if you're training with 80 samples, 80 different observations, it will predict perfectly for all the 80 samples because it has seen all the 80 samples, right? But when it sees a new sample, it will fail miserably because it has only tried to fit specifically to this training set. And that is exactly what is called as overfitting. Regularization is a way to avoid overfitting. So what we do is, regularization is basically a penalty term that is added to your function, right, which kind of balances out the overfitting issue, right? So here in this case, c equals to 1.0 is a regularization parameter, which it's a penalty parameter basically. So if you do not add this, you will see the danger of not doing standard scalar and the danger of not adding a error parameter, a penalty parameter here. If you don't do that, what will happen is something that we will try to follow. Okay. Then once you create the model, you're fitting it to your data. So you took the standardized parameters, you fit the standardized parameters, you try to predict the model, you tell it that, hey, this is the target I'm trying to predict. Okay. Then color is equals to black. So this is a simple, what do you call, piece of code where once I get the prediction, right, I'm trying to color these two data sets. Okay. So depending upon what my label is, I am coloring them. So if it is 0, I'm coloring them black. If it is 1, right? So this code is basically that. If C is equals to 0, it's black. Else it is light gray. And that's how these couple of points I end up coloring as black. These couple of points, these couple of species, I end up coloring as light gray, right? Then I solve for the hyperplane. So I fit the model already to the data, right? I use the fit function. I fit the model. And once I fit the model, I look at the coefficients, right? Question here. How many data dimensions does my data set itself have?
Isn't it 2 in this case?
Correct. 2, right? Because we are selecting 2 here, right? Now, if if the dimensions of my data set are 2 in number, what is the dimensions of my hyperplane?
1.
Correct. 1 dimension means a line, correct? Y is equals to mx plus c. The nature of y is equals to mx plus c. And that's exactly what you get here. When you fit the SVC model, you get this blue line, right? Now, how do I plot the line? I fit the model already. So the model is here, SVC, right? So what I do is SVC dot coefficient underscore 01 will basically give me the coefficient. So as I said, right? So the equation, my equation is y equals to mx plus c, right? This is my coefficient. This is my intercept. Okay, so when this is the equation of straight line, this is a coefficient and this is intercept. After I fit my model here, I will look at coefficient here. Okay, so we are using A basically to calculate the intercept. Got it. So A is basically my variables. Then okay, I'm creating the hyperplane here, right? So A into XX. X is basically my this variable. I'm picking the coefficients, and then I'm picking my intercept, right? So these are two different. So when I pick the coefficient, right, I getting two different numbers. When I divide them, I get A. I multiply A, which is my new coefficient, with X value. So I am drawing a linear space, drawing samples from a linear space, and then I add the intercept here, divide by W of 1. Once I get that, I plot it, right? So then I get this blue line. This is my hyperplane. Okay, so one quick notation here, one quick point that I want to tell here. You won't have to do this in case of your data set. You just have to print your coefficients. The reason why we are doing this is we are trying to visualize the data that we have here in a visualization. Usually what happens is you will have multi-dimensional data sets. You won't have to create visualizations because it won't be possible for you to create a visualization, right? Because it's n dimensions, you won't have to create a visualization. So you won't have to do this exercise of pulling these things out. You can just see what are the coefficients. That way, what the coefficients do is they tell you how much influence a specific parameter might have on the prediction. So what I mean is, yeah. So here, right, mx plus c, this is my coefficient and this is my intercept, right? So if, let's say, if my m value here is very close to 0, okay, it's very close to 0, what happens to my y values? So if m value is very close to 0, what happens to my y values? Okay, let's assume that it is 0. If m is 0, okay, what happens to my y values every time? If this is 0, what happens to my y value? It is equal to c in every case, right? Because x doesn't matter anymore, right? Okay, in order to give you guys a even better example, let's say this equation, right? I'm writing this equation. If you guys remember the example from last class, I am trying to, let's say, predict the price of a fabric. Okay, assume this hypothetical example. I am trying to predict the price of a fabric. This is my y value, y variable, based on the cost of cotton. Okay, this is my x value. Okay, and I'm assuming that at this point that my price of fabric is only dependent on the cost of cotton that I'm buying. Okay, so cost of cotton is x, price of fabric is y, and I am trying to model a relationship like this: y is equals to mx plus c. Okay, and I found out that m is equals to 0. Let's say m value is 0. What happens then? In any case, let x take any value, let the cost of cotton be anything, y will always be c, right? Because when x is 1, it doesn't matter, 2, it doesn't matter, 3, it doesn't matter, because it's always getting multiplied by m, which is 0. Guys, did you get that? It's a simple equation of a line.
Yes, sir.
Simple function, right? So when my coefficient or my m value is 0, it doesn't matter what my x value is, it will always be 0, because the product will be 0 and y value will always be c, right? So what that would mean is let's assume in this case, right, my M value, I fit a function, I drew a line, I fit a function, and M value is 0. Okay. Now, if my price of cotton is $10 per pound, right, and let's say C is equals to 15. Okay. Can you tell me what is the cost of a fabric if the cost of cotton is $10, and given that this is my equation, right, what would be the price of my fabric? Did I hear something for someone?
15.
Correct. That is right, because it's Y is equals to C in that case. Correct. Okay, let me assume that my cost of cotton went up. Okay. Now I am purchasing cotton for $20 per pound. What will be the cost, the price of my fabric now?
It's still 15.
Exactly. So it will always be 15, right? Irrespective of what my cost of fabric will be. Now, what does that mean? Is my price of fabric really dependent upon cost of cotton?
No.
Right? It's not dependent, because even if my cost of cotton is 10 or 20 or whatever it is, right? My cost of the price of my fabric is always $15. It's never more or less or anything. It's constant, right? So that is the significance of coefficient M, right? So let's assume that M is 1, okay, instead of 0, M is 1, okay, and this is 15, the same as it is. If my cost of cotton is 10, what will be the price of my fabric?
150.
115. Why?
15 and 10. Oh, some, not small, not product. Sorry.
Yeah.
I take that back. 35.
So, well, here's the final plot basically that we have is this line dividing these two data points. So what I want to do now is very same code. I want you guys to like run it in your local systems. Okay, so I'll provide you with pieces of code. This is the notebook that is there on Refactored. I want you guys to like look at it. If you want to look at it, you can look at it and then do that. Okay, by the way, let's go back to what we were actually discussing and wrap that out. So I was talking about the coefficient, right? So if my coefficient was 0, that basically meant that my so y is equals to mx plus c. If my coefficient is 0, then the cost of cotton really didn't matter, right? Which means cost of cotton never had an influence on the price of fabric, right? If the coefficient was 0, when it was 1, there was some influence. There was a very linear relationship. As my cost of cotton increased, my price of fabric went up by that much, correct? Because C was constant at $15, but when cost of cotton was $10 per pound, the cost of fabric was, okay, let me just draw that. So this was 10, this is 25. This was 20, this was 35. If this was 30, this would have been 45, right? So if you see, it's very evenly matched, right? You're just adding $15 more to the cost of cotton, and then you have your price of fabric, right? So it's a very linear relationship when M is equals to 1. Even when M is equals to 2, it's still a linear relationship, but things keep doubling, right? As your price is, it's 10, then it becomes, if let's say M is equals to 2, right? This will become 35. This will become 55, right? And this will become 75, right? So it will basically keep doubling if M is equals to 2, and then you will still add the $15 at the end, which is our intercept, right? So this is how it would proceed depending upon what the value of M is. Okay. And that is the reason why M, or the coefficient, determines the amount of influence a particular predictor has on your target value. That's what we mean. So here, cost of cotton is my predictor. We are trying to predict the price of my fabric using the cost of cotton, right? And M basically tells me how much effect or how much influence this predictor has on the target variable. Makes sense now about coefficients?
Yeah.
Clear, right? Cool. Awesome. Now, the same thing, right? I want to tell you about what happens when you have multiple predictors, right? So let's assume that I have a new case. I have more data, right, about the price of fabric, right? So I have Y, which is the price of fabric. X1, which is cost of cotton, and X2, which is cost of labor, right? Basically, which means that someone is taking the cotton and they're stitching it out in the form of a fabric, right? Someone is converting my cotton into a fabric, right? So in this case, right, Y will be equal to M1 X1 plus M2 X2 plus C. It could be something like this, right? Now, here in this case, right, M1, the coefficient of X1 tells us about the influence of which variable?
X variable.
X variable.
Yes, X1, correct. But what is this variable? What does this signify?
Cost of
The
cotton.
cost of cotton.
Correct, right? So M1 tells me how much influence cost of cotton has on my price of fabric at the final, when I finally decide how much I have to sell my fabric for, right? How much of what I decide here depends on the cost of cotton is told by M1, the coefficient, right? M2 will tell me the influence of X2 on Y, which is the cost of labor, right? So let's say that, for example, cost of cotton has a certain influence, but cost of labor is much more expensive. And that's why the price at which I'm willing to sell my fabric depends a lot more on cost of labor than the cost of cotton, right? Let's assume that case. In that case, M1 would be something like, say, 1.64, and then M2 could be something like 3.56 or something like that, right? Relatively. If these are the numbers that I'm seeing as coefficients, what does that tell me? This has higher influence than this on my end result variable. Okay, 3.56 as compared to 1.64. Does that make sense? Clear? Now, intuitively, I'll ask you a question. Okay, let's say my M2, right, is this won't be true in reality, but let's assume this is minus 3.24. What does this tell you? Minus 3.24. Any guesses, anyone? So the influence is in magnitude definitely more than the cost of cotton. But what does the minus sign tell you?
Negative influence on the.
Absolutely correct. Perfect. Negative influence, which means what does that actually mean? Negative influence mean, right? There is a relationship, right? Like there is direct proportionality and there is inverse proportionality or inverse relationship. Negative influence is nothing but an inverse relationship, right? Which means, so if it's positive, right, what happens? If my price of cotton, the cost of cotton goes up, my price of price of fabric also will go up, right? But inverse relationship means here, if it is minus 3.24 in this case, M2's case, the cost of labor goes up, price of fabric will come down, right? Because it's negative in influence. That's the inverse relationship. So whenever you see a negative coefficient, know that the relationship is inverse. If the predictor increases, the target will decrease. If the predictor decreases, the target will increase. It has a negative relationship with the target or negative influence on the target. Okay, makes sense? But again, you can't imagine this being true in real life, right? You can't imagine that cost of labor is more and I'll sell my fabric for low, right? So that most probably won't be true in real life, but there might be some other variables, right? Some other features. What can I think of? Let's say government subsidy. Okay. Government subsidy. Okay. Government subsidy, or even better, right? We could look at another variable as well. Cotton production, right? How many tons of cotton is produced, right, in a given year? Let's assume that's one variable. Now, if you guys can think of it, what happens when my cotton production goes up? Like, let's say this year, all of Massachusetts or all of Texas has basically produced like 20 million tons of cotton, right? What would happen to the cost of cotton? When I have a lot of cotton on the market, what will happen to the cost of cotton?
Go down.
So
Correct.
it would-
Yep, it would go down, right? So when I have too much cotton production, the cost of cotton will go down. And when the cost of cotton goes down, the price of fabric also goes down, right? That is where the coefficient might actually be a negative number like this, right? Or think of a government subsidy. Let's say government has subsidized the prices or the cost of cotton. It says that, okay, 30% of the cotton is something that the government will, cost of cotton is something that the government will bear, or reduce taxes for the fabric or whatever, right? That will also negatively influence the price of my fabric, because the higher the government subsidy be, the lower my price of fabric can be, right? If the lower the government subsidies that I get, the higher my price of fabric will be, right? Make sense, folks? Right? So this is how coefficients and equations basically work, right? So even here, right, like once you get a function, once you get the function of your, once you figure out the function of your model or the support vector classifier or regressor, you will have these coefficients and the intercepts. Coefficients are the ones which will help you understand the influence that each predictor have on the target variable, right? Whatever you're trying to predict. So there's a clear group of red points, there's a clear group of green points, right? If I draw a line like this, a black line between them, right? This can become my classifier or my decision boundary or my hyperplane, right? Hyperplane,
Yeah.
right? But what happens if my data doesn't look like this, instead like this? Okay. What happens when my data looks like this? How am I going to draw my line, black line? It's overlapping, right? So the data is heavily overlapping. So there are green dots, there are red dots, all in between each other. How am I going to draw a decision boundary that actually separates these two, groups of data, and then gives me a nice division, Nice. And that the reason why I'm trying to draw that black line is to separate these two spaces and say that when I get a new point from a specific space, is it a red point or is it a green point? That's what I'm trying to do with classification, right? But here, how do I even draw a line in order to separate these spaces, because they're so overlapping with each other so much, right? This is where kernel tricks really work. They help. What they do is they help in transforming the data to a different dimension, right? Transforming the data in such a way that you can end up separating them. For example, this specific data, right? So what happens is I end up getting this data points like this. So what happens is, let me move this a little bit. Okay, now this is in two-dimensional space. What I achieve with kernels is I draw this in three-dimensional space, right? So earlier, so this is X and this is Y, let's say. So this is X and this is Y. Now, what I do with kernel tricks is basically I introduce a third dimension Z, right? Where if I look, so let's say this is X and Y, right? If I look from, this is my X and Y. If I look from the top, right? These data points look like they are overlapping on each other, right? The red and green ones, because they are in the same space, right? So if I look from above, the red and green points can look like they are overlapping with each other, right? They are like this in a two-dimensional space, but in a three-dimensional space, I can draw the Z dimension using a kernel trick, and then I separate these two clusters out, and then I draw a plane between them both, separating them both. Right? This is a plane that cuts these two data sets. Understood that? Do you get the idea of kernel tricks?
Yeah, kind of.
Yep. So let me quickly look at SVM, right? When you just type that in Google, you'll be able to see some images. Okay, it's loading up. See this? Input space, feature space, right? So it looks like in a two-dimensional space. If my input space is two-dimensional in nature, and there is overlap between my two different groups of points, right? What I do is I use a kernel trick to convert it into a three-dimensional space, in which case so if you look at these same points from above, right, disregarding the third dimension, which is height, right? If you just look at them in a two-dimensional form, they might look overlapped, but when you increase the dimension, when you add another dimension, there is a way for you to separate these two groups out, and then you can draw a line to do that. So again, this is the same thing, this is the same thing, all of these are like same. So look at this is even better, right? So the data looks like this. It looks like two rings, right? These are red points on the center. The blue points are all around it, right? How do you even draw any structure which separates these two groups out, which classifies these two groups? Now convert them into a three-dimensional structure. See, all the blue points are on the bottom, or the red points are on the bottom, the blue points are on the top, or something like that, right? Now here there is a gap in vertical space. This is where you can draw your plane which separates out these two points like this here. Making sense?
Yeah.
What you cannot do in 2 dimensions, you can possibly do in 3 dimensions. That's basically what kernel trick does. It helps you transform your data or add more dimensions to your data in order to pick it up, put it in a different dimensional space, and then slice your data accordingly. Okay. Clear, everyone? And okay, one more point that I mentioned in last class, I'll mention it for the benefit of everyone who hasn't heard about it. SVMs are good at dealing with multidimensional data. Okay, because you can have the possibility of having n different dimensions in your data, and then you can come up with a hyperplane which is just n-1. The model will be a little complex, but it is still good at handling multidimensional data. Okay, so keep that in mind whenever you encounter a data set with a lot of columns, a lot of variables influencing your target, you can go for an SVM. And although it might come up with a very complex model, it will still work. Okay. All right. That's it for today's class.